This is the recursive algorithm. This is a legitimate algorithm that says yes or no on every one of these inputs. I say switch your answers around. Do the complement trick. Make your yeses no's and your no's yeses. Then what set does your new machine that I told you to switch around, what does it accept? It says yes to all the Turing machines that don't accept themselves. So the existence of this assumption implies that there really is a Turing machine that says yes to all the Turing machines that don't accept themselves. It's just the toggle of your Turing machine. But we just convinced ourselves that that Turing machine that accepts all the others that don't accept themselves, that doesn't exist. But it would exist if we had this thing around. So it's a contradiction, this assumption. This assumption contradicts the fact that this doesn't exist. So I'm going to write this down a little more carefully. This doesn't exist. That's by the Barber argument. And the fact that that doesn't exist, this assumption implies, let's call this, I'll give this a name. I'll call it weird set. The weird set doesn't exist, and this algorithm implies that the weird set does exist. Why does it imply that the weird set does exist? Because just take whatever algorithm you use here and switch the yeses for no's. So this assumption implies that weird does exist. All my logic implies that weird doesn't exist. So this assumption's got to be wrong. That means there's no algorithm at all that tells me whether M accepts X. That means that this problem is undecidable. So that's the end of the proof, and that's the proof. We have our first kind of like original sin here. This is the first problem that you just can't do. No way to do it. And it's really, really based on this little trick. So let me stop for a second. This is exactly actually the way our book does it, in principle. There's other ways to prove this, all essentially equivalent. They might not seem equivalent to you at first reading, but they really are. And our book does it just this way. It assumes the existence of this, implies the construction of this table, derives that this set can't exist if this table exists, and then says, but this implies that that set does exist, so this can't ever be a reasonable assumption. Therefore, there's no algorithm that is magic that does the halting problem. It doesn't exist. So this is different than the finite state machine level. Here we have to make an assumption of something existing and then showing that it didn't exist. Before, there really was a Turing machine that did it, and all we got as a result was that there was no finite state machine. But here we got that there was no Turing machine by this extra little trick. Let me stop for a couple minutes and let you ponder this and ask some questions. Let's look at that again. This is a magic halting algorithm. I give you a Turing machine and an input, and you tell me, does that Turing machine accept it? You say yes if it does, and you say no if it doesn't. I don't know how you do it, but you've got it. And I say, go back to your program, and every place where there's a line that says, you know, yes, change that to no. And every place there's a line that says no, change that to yes. So now your Turing machine is going to say yes every single time the other one used to say no. Yeah.
Now this is because of the fact that we've defined computability to be the things that Turing machines can do, and therefore for an algorithm to exist, it has to be computable by a Turing machine.
Yes.
So conceivably, if we were to broaden our notion of computability outside of that realm, then this might not be a problem.
That this wouldn't contradict that.
It would be akin to
moving out of town again. Right. So Neil asked before, can you move out of town again? And Chris is asking this in a more rigorous way. Can you go ahead and broaden our sense of computation to go beyond a Turing machine? Sure, a Turing machine seems to model computation, but it doesn't seem to model the way I decided who I was going to marry, for example. I don't think anybody was going to write a Turing machine to do that and consistently print yes or no to successful marriages. There seems to be some quantum emotional biological response, and everybody manages to pick the right mate. No. The point is, it is possible that there are levels of computation above Turing machines. There can be quantum computers, perhaps. There could certainly be computers that work on some randomness or some kind of level that's beyond the deterministic, step-by-step mechanistic level that we assume Turing machines are. And if that was the case, then it is possible that one of those computers could really answer this question and then wouldn't have an issue with contradicting itself because it wouldn't be in the group under consideration. That's possible. Yeah.
Which, of course, just expands the problem.
It just expands the problem to the next level, right?
Yeah, I guess that's my next question. Is there any hope ever?
No, there's no hope. No, there's no hope. No, we fundamentally cannot compute things, period. You come up with your model of computation, and there will be questions about that model that model is not powerful enough to compute. It's always the case. That's what diagonalization says. It says that these machines are not smart enough to be completely self-aware. And that's just the way it is.
And any machine that we could construct that is completely aware about these
Wouldn't be aware about its own members completely. Right. Right. And I think we're just computers, and we count too. We're also not completely self-aware. It goes the same way. But not everybody thinks so. Or do I?
Why doesn't it work at one layer down on the FSMs, this magic algorithm? Why can't you do that?
You can do this. This magic halting algorithm exists.
Yeah.
I mean, there is a Turing machine that will say yes or no whether a finite state machine accepts himself. There really is. But that Turing machine is outside of the realm of finite state machines, so it doesn't have to accept itself or not accept itself according to that Barber criterion. But there is no finite state machine that can do that for finite state machines, and that is exactly the same reasoning. In fact, the only reason we got past this subtlety with finite state machines is because I told you we created this table using a Turing machine for finite state machines. If finite state machines were the limit of our computation, you would have stopped me right there and you would say, well, how do I make this table? Finite state machines can't make that table. Or can they? And at that point, the argument would have been identical to what we just did here. The only reason the argument is a little different is because we get to the frontier of what we think is computation. And the question of just coming up with this table is the same as the question that we're trying to show can't be done. So you get this kind of backhanded proof. Yeah, Joe?
Why can't you move the machine inside the finite state machine? Make it a finite state machine to read all Turing machines, since it's like a separate town.
It's inside.
You mean the Turing machine that accepts finite state machines that don't accept themselves? Why don't I move it inside the town?
The Turing machine that accepts all Turing machines that don't accept themselves.
Well, there isn't any Turing machine that does it. Right.
But I mean, if you
Yeah.
moved it to the finite state machine level.
But all finite state machines are also Turing machines.
Okay. I'm not sure I understand the question or the answer, but I know there was communication. It's like, it's my happiest moment as a teacher, when two people seem to communicate, understand the material better than before, and I have no idea why. That's the way. Good. Whew. All right. More questions about this?
Does this correspond to the fact that any mathematical axiomatic theory, there will be questions which you can't answer?
It's very similar. It's not exactly the same proof, and the proof for that is different, but the notion behind it is similar, and it's for the same reason. Yes. It's very similar.
Which proof came first?
The one that Sham just said, yes, that came first, I'm pretty sure. Yes. That every mathematical system that's powerful enough to describe the rules of arithmetic has statements that are true, which cannot be proved one way or another within the system. That is, look, if this is a little confusing, I think that's more confusing. I really think that that's harder to get. I don't know. I think it's harder. This is, maybe I just thought about this more. All right. There's a lot we did today, but there's also a lot we didn't do. Let me give you a little heads up on where we're going. We've been going for a while. I'm not going to do anything more complicated. I'm just going to tell you what we're going to do next time. We finally proved that we have a legitimate problem that's undecidable. If I give you a machine and a string, and I say, does